I totally forgot that we did not complete all the exercises after that portion named coordinates, lines and increments. In fact, we kept the solution to exercise 52 also incomplete, and that exercise asks us, let us recall this. Say we have a point x comma y in the plane that undergoes a rotation, anti-clockwise rotation or counterclockwise rotation through an angle 90 degree, where the center of rotation is the origin. We are being asked here to find the coordinates of the final position of this point. We in fact did something here. We did precisely this. So we located the point, original point, which may be anywhere in these 4 quadrants. First of all, of course, we took care of the situations, what happens when the point lies on the axis. Then the next thing is that we considered our point to not lie on any of the 2 axes. Say the point lies here. What we then did, we calculated the equation of the line that passes through the given point and the origin. We found its equation. Then using that equation, we found the equation of the line that passes through the origin and is perpendicular to this line. Then using the fact that after that rotation, the final position of this point will also be at the same distance from the origin as the initial position. We used this thing to finally found a condition, and we ended up with 2 possible choices for the final position of the point. One of them is this and the other one is this, or I am writing because one of them is going to be our answer. So after this, in the solution you write this. Looking at the 4 cases, depending on which quadrant contains our given point. So our given point may either lie in the 4th quadrant or 1st or 2nd or 3rd. And these are the 4 cases. We find that the rotation takes x comma y to minus y comma x. So these are the coordinates of the final position of the point, and the solution actually ends here. So let us now continue with the other exercises. Once we, not many are left, once we solve all of them, we will go back to our usual study of functions, and there we will continue. So exercise 53. For what values of k is the line two x plus ky equal to 3 perpendicular to the line 4x plus y equal to 1. So that is 1/2. For what values of k are the lines parallel? That is the other half. Are the lines the lines means those same two lines, I mean these two equations. The slope of 2x plus ky equal to, but before we find the slope we need to make sure that k is non-zero, because otherwise we won't be able to divide by k. So let us consider that case first. The straight line if k is 0, then the straight line is this, 2x is equal to 3. This straight line is vertical, and this clearly is not a horizontal straight line, neither is this a vertical straight line. So this straight line is neither parallel to this nor perpendicular to this. The straight line is neither parallel nor perpendicular to 4x plus y equal to 1. Okay. So assume k to be non-zero. So we are no longer considering this vertical line 2x equal to 3. Whatever our line is, it's not vertical. Then the slope of the straight line 2x plus ky equal to 3 is, if you manipulate the equation a little bit, bring it in the form y equal to mx plus c, then reading of m you get m is minus 2 divided by k. Just like that, the slope of the line 4x plus y equal to 1 is minus 4 y equal to mx plus c. So 2x plus ky equal to 3 and 4x plus y equal to 1 are perpendicular to each other if and only if the product of these two slopes is minus 1. or if and only if. So what do we get? 8 divided by k is minus 1. So k is equal to minus 8. And two x plus ky equal to 3 is parallel to 4x plus y equal to 1. If and only if the slopes are equal. Or k is 1 over 2. So these are the values of k that give us that make the lines parallel and perpendicular to each other. Next, (54). Find the line that passes through the point 1, 2. And through the point of intersection of the lines x plus 2y of the two lines x plus 2y equal to 3 and 2x minus 3y equal to minus 1. Okay. So that means 2 points are given. One is explicitly given, its coordinates are given, the other is given indirectly, namely as the point of intersection of these two lines. So we have to solve these two equations and find that other point. Can we do it somewhat quickly? Or in fact, let's just make it a part of the solution. If the points, or if the point of intersection of the lines x plus 2y equal to 3 and 2x minus 3y equal to minus 1 is x naught comma y naught, then x naught plus 2y naught equal to 3, like that 2x naught minus 3y naught equal to minus 1. this implies okay, so 2x naught is 3y naught minus 1. So if we multiply the first equation by 2, then we get this 2x naught plus 4y naught equal to 6, which implies now in place of 2x naught we can substitute this 3y naught minus 1 plus 4y naught equal to 6, and that implies 7y naught equal to 7. 6 plus 1 is 7, which further implies y naught equal to 1. So y naught must be equal to 1. So from the first equation we see that x naught then must be equal to 1 also, because if y naught is 1, then 1 plus 2 should give us 3. Hence x naught is also equal to 1. So the coordinates of the point of intersection of these two lines are 1, 1. So we have to find the equation of the straight line passing through 1, 1 and 1, 2. So let us find the, in fact from the values of these coordinates you can see one thing. One of the points has coordinates 1, 2 and the other has coordinates 1, 1. The points must be on the same vertical line. Okay, so the equation actually will be x equal to 1, which of course you will also find, you will find the same thing if you follow the point slope form of the equation. That way also you can do, but oh wait, slope you cannot find because the line is vertical, so slope will be undefined. So instead let us write like this. So the straight line we are seeking is the vertical line passing through 1, 2 and 1, 1. We have already seen that 1, 1 satisfies this equation. Does it also satisfy? Yes. Okay, so there is no mistake in this value, and hence its equation is x equal to 1. That's the thing, that's the solution. Then exercise 55. Show that the point with coordinates x1 plus x2 divided by 2, y1 plus y2 divided by 2 is the midpoint of the line segment and x2 comma y2. So we just need to calculate the distance between this point and any one of these 2 points. If that turns out to be half of the distance between these 2 points, then it becomes the midpoint. Note that the distance between, say, the first one and this one, and this, is, so we apply the distance formula. Since it's difficult to write square root this way, we will write to the power 1 by 2. x1 plus x2 divided by 2 minus x1 square plus y1 plus y2 divided by 2 minus y1 whole square root of this entire thing. So if we take LCM and do all the simplification, then we get x2 plus x1 minus 2x1 is minus x1. Just like that, y2 minus y1. So you can see that after squaring and taking 1 over 4 common out and then taking square root of that, after everything has been done, we are left with this. Square. And note that this is nothing but the distance between this point and this point. So that's it. So the distance between this and this is half the distance between this and this. So in fact we can write this is equal to of the distance between hence you can now write the final sentence. Hence the point with coordinates is the midpoint and so and so. So I am ending here itself. Finally, I think this is the final one. The distance from a point to a line. So this exercise gives us a procedure, or it tells us the steps that we can follow in order to find the distance of a given point from a given line. We can find the distance from a point P with coordinates x0, y0 to a line L which has this equation ax plus by equal to c by taking the following steps. There is a somewhat faster method, okay. In section 10.5, which of course we will see when we get to that part. So the first step is this: find an equation for the line M through P perpendicular to L. Second step, find the coordinates of the point Q. In which M and L intersect. And the final step is find the distance from P to Q. So the situation is like this. Here you have a point, here you have a line, a straight line. You should not think, okay, let me draw it somewhat differently. Let me draw it here. You have a straight line and you have a point. This line is L, this point is P. Coordinates of P are given, the equation for L is also given. First, what you do, you find the equation of the line that is passing through P and is perpendicular to L. Call that line M. Then find the point of intersection of M and L, that is this point. Then find the distance between Q and P. So that will be the distance of the point from the line. Now use these steps to find the distance from P to L. in each of the following cases. Part A, P is this point and L is this line, y is equal to x plus 2, having this equation. Part B, P is the point 4, 6 and L is the line 4x plus 3y equal to 12. Part C, P has these general coordinates a, b and L is the line x equal to -1, and part D is the most general, of course, where P has the coordinates x0, y0 that it originally had, and L is this general straight line. Okay, so we will solve only part D, so automatically the other parts will be solved, they will follow from this. So essentially we will find a formula for this distance, because here the point is general and the line is also general, and steps are given, so we are going to follow the steps in that order in which they are given. So first of all we have to find an equation for the line M through P perpendicular to L. But cases will arise. Okay, let us first start by mentioning that we are doing only D. We solve only part D. The other parts follow from this. So to find the equation of the line M that is perpendicular to this line and is passing through this, we need to know about its slope. If the line itself is perpendicular, namely if B, capital B is 0, so that is the first case. If B is equal to 0, L is if the line is vertical, okay, perpendicular is that word is used when we are talking about the relationship between two lines. If the line is itself vertical, then B is 0, and conversely, then L is vertical. So the equation of the line M, that is perpendicular to L and passing through Px0, y0 is L is vertical, so the line perpendicular to it, M will be horizontal, and for the horizontal line that passes through this point, the equation is y equal to y naught. So we now have to solve these two equations, this one and this one, when b is 0. Solving the equations y equal to y naught and ax equal to c. Okay, so if y is equal to y naught and ax equal to c, so if we put y equal to y naught here, then x becomes c divided by a. Yes. So the point of intersection Q has the coordinates Do you see how we are able to divide by a, although we haven't said anything about whether a is 0 or non-zero? L is a straight line and already b is 0. In this situation, if a is also 0, then c is 0 and we get an equation that looks like this: 0x plus 0y equal to 0. That is not the equation of a straight line. So because b is 0, a must be non-zero. But we are, however, not mentioning that here. So it makes sense to divide by a. So this is the these are the coordinates of the point Q, which is the intersection of L and M. Now we have to just find the distance between P and Q. Okay. Between P and Q is this: square root of x naught minus c by a square plus y naught minus y naught square. So this vanishes and we are left with, if we cancel square and square root, we are left with this. Okay, so that is one case. And now we consider the case where b is non-zero, so that our line L is not vertical. If b is non-zero, then the slope of L is ax plus by equal to 0 equal to c. So you can rewrite the equation like this: minus a divided by bx plus c divided by b. So it's of the form y is equal to mx plus c. So here the slope is minus a divided by b. So the equation of m is perpendicular to this line, so its slope should be the negative reciprocal of this. Okay, but there again, okay, still we have to take care of one more thing, namely we cannot take the negative reciprocal if a is 0. So that case also has to be handled separately. It is longer than I was expecting. If a is equal to 0, L is horizontal. So m, which has to be perpendicular to L, now m is vertical and m passes through the point Px naught comma y naught. So m is the vertical line passing through Px naught comma y naught, and its equation is x equal to x naught. Okay. Now we have to solve again two equations: x equal to x naught, that is the vertical line m, and the horizontal line L, whose equation now is by is equal to c, where because now a is 0, capital B is not 0, otherwise it won't be a line. Solving x equal to x naught and by equal to c, we get x equal to x naught and y is equal to c divided by b. So the point Q of intersection of L and M has the coordinates x naught comma c divided by b. The distance between P and Q in this case is this. Minus c divided by b. Now we can consider the case where neither capital A nor capital B is 0. Both are non-zero. Next, assume that A is non-zero and B is also non-zero. I kind of don't want to lose this value as well as this distance, because in this third case we are going to get a formula which hopefully will also shed some light on this particular cases if we take into account everything cleverly. Let us see what we mean by these things. The slope of the line L is, again just like before, ax plus by, so this is minus a divided by b. Hence the slope of the perpendicular line M, this time that slope of M is also defined because L is not horizontal. This is b divided by a. So the equation of M is, we know the slope of M, we also know the fact that M passes through the point P, so we can use the point slope form of the equation times x minus x naught, or y equal to y naught plus b divided by a times x minus x naught. Now we have to solve this equation. This is the equation of M and the original equation of L. We now solve the equations of L and M. That's why I have kept it in this form, so that we can substitute this expression for y in the equation for L. We have ax plus by equal to c. So in place of y we are going to put this. So this implies what? Ax plus by naught plus b square is coming. Anyway, whatever comes will come. B square divided by a x minus b square divided by a x naught equal to c. So we take all the x terms together, this and this, that is a plus this times x. So we have considered this term and this term, and we are left with what? Minus b square divided by a x naught plus by naught plus by naught, okay, equal to c. A square plus b square x is equal to, if we take the things on that side, we get b square divided by ax naught minus by naught plus c. Now if we multiply on both sides by a, what do we get? In the first term, a and 1 over a, they will cancel each other, so we will have a square plus b square times x equal to b square x naught minus ab y naught plus a c. The calculation will continue. This one also I am keeping, okay, for verifying later the special cases. So our x now becomes b square x naught minus ab y naught plus ac divided by a square plus b square. Note that since a and b are both non-zero, so this cannot be equal to 0. In fact, even if one of them is non-zero, then it is non-zero. So this is our x. We are now going to substitute this x here in this equation to find the corresponding value of y. Now y is equal to y naught plus b over a into x minus, we should do it very carefully. There is high chance of making mistakes because of abundance of symbols. A square x see, I have already made a mistake. It is I am putting this expression for x, so it is this minus x naught. Minus a square x naught minus b square x naught. Do we have any simplification? Oh yes, b square x naught and b square minus b square x naught, these two things cancel. This one and this one, and we are left with ac minus a square x naught minus ab y naught, but we have to still continue the calculation. If I do so, the things will be very complicated. Okay. X has come out in this form, fine, and y has come out in this. Okay, let's not just continue it anymore. So the coordinates of q are, in this case, these b square x naught minus ab y naught plus ac divided by a square plus b square, comma, it looks very bad, but it is what it is. And I have decided not to mix this y naught up with the other things, because when we are going to calculate the distance between this point q and p, there we have to subtract y naught from this, so those two things will cancel out. AC minus a square x naught minus AB y naught divided by this. Now our final job is to calculate the distance between P and Q. So this minus x naught, b x naught, b square x naught minus ab y naught plus ac divided by a square plus b square minus x naught square plus this minus y naught squared. So y naught won't remain, and since we are taking squares, so we will have b square divided by a square times ac minus a square x naught minus ab y naught divided by this and square root of this. Now it's time for simplification, which we have to skip some steps in order to save space. After taking LCM and after simplifying this expression, you see, we will be left with a square x naught, that to be the minus sign, and minus b square x naught plus b square x naught, they will vanish. So that means here we will have minus a square x naught minus ab y naught plus ac square divided by a square plus b square whole square. So this is the first square, and the second square of course is this. Oh, so we are in fact getting the same thing. AC minus a square x naught minus ab y naught whole square divided by this, but along with that we have b square divided by a square. So we have common terms to take out, and the common terms are these: AC minus a square x naught minus ab y naught divided by square divided by a square plus b square whole square. So in the entire first thing, you are wondering, here we have minus a square, no, actually we do have exactly the same thing, no, just we have written them in slightly different order. Here AC has been written as the third term, here AC is the first term, that is the difference. So the first term itself is common to both the terms, so we are left with 1 plus this, and there is a square root. Okay. Okay. Now if we simplify this, then in the numerator here we will have a square plus b square, that we can cancel with 1 a square plus b square here. Why? Because a square plus b square after all is a non-zero real number, a positive real number. So keeping the square root as it is for now, 1 a square plus b square gets cancelled, 1 a square plus b square remains. In the numerator we want to write the things in a slightly different manner. What we do, from these, all you see in all of these terms there is a, we can take minus a common out. When that minus a meets square, minus a whole square becomes a square, and inside we have a x naught plus, since we have taken minus a common out, b y naught minus c whole square. Okay, so these two things then cancel each other, because keep in mind that not only is a square plus b square non-zero, in this particular case both a and b are also non-zero, so a square is non-zero, so they cancel each other, and the distance becomes this. This is equal to, now if we take square roots separately, we have ax naught plus by naught minus c divided by square root of a square plus b square. Okay. Now what happens to these special cases? This is the distance between p and q when our original when a is 0, and this is the distance between p and q when b is 0 and hence a is non-zero. Now what happens if we put a equal to 0 here? We know we cannot put a equal to 0 here, because the way we have derived this equation, or rather this formula for the distance, our assumption is that a is non-zero, b is also non-zero. So from that point of view we cannot put a equal to 0 here and claim that that is the distance. However, we can just simply put a equal to 0 here in this expression, and then we want to see whether this formula reduces to this formula. If so, then we can write only one formula for the three cases. It is much more nice. So putting a equal to 0, what do we get? The distance becomes by naught minus c divided by b, because this one vanishes and square root of b square is just the absolute value of b. From the properties of absolute value, this becomes so yes, we actually get this formula. what happens when b is equal to 0 and a is non-zero? In that case, the formula for the distance becomes a x naught minus, you can pretty much see that the similar thing will happen in this case. Okay, so the same formula can be used in all the three cases. Let us now going to mention that fact also to complete the solution. Note that when a is equal to 0, the distance between P and Q that we calculated to be is also given by the above formula. If you want, you can give it some sort of number. Also gives the distance when b is equal to 0. So in general, the distance between P and Q is this. Okay, so it sort of becomes a formula. You have the equation of the line ax plus by equal to c, and you have the point from where you want to find the distance x naught comma y naught are the coordinates of that point. Then this is the distance from that point to that line. Okay, so here the solution ends, and this set of exercises properly ends. It's completed in its entirety. Okay, now we go back to functions. We have already seen the many things related with the notion of a function. We have seen what the domain and the range of a function are, what a dependent variable and independent variable are, and many other things, how a function is to be interpreted as a sort of machine or as a sort of rule that associates each element in the domain to a unique element in the range. Things like that we have already seen. Now the next thing is evaluation of functions. As we said earlier, most of the functions in this book will be real valued. Although a general function may have any sort of input, any sort of objects as inputs and any sort of objects as outputs, but the functions we will be interested in this book, they are going to be real valued functions. Most of the functions in this book will be real valued functions of a real variable. Real valued means the outputs are real numbers of a real variable. This variable is the independent variable x, so the inputs are also real numbers. May not be all real numbers, but whatever they are real numbers. That is, functions whose range and domain are some sets of real numbers. We evaluate such functions by substituting values particular values from the domain into the functions defining rule or defining formula. To calculate the corresponding output value in the range. And there are, of course, evaluation is something which is very natural and easy. Evaluation is actually what a function does. Okay, it tells you what the output is for a given input. The process of calculating that output value for a given input value is what evaluation is basically. So we see example 1. The volume V of a ball is a sphere, solid sphere of radius r is given by this function. It's a formula with which you are probably already familiar from your solid geometry. From geometry in 3 dimensions, Euclidean geometry in 3 dimensions. There this formula is available. The volume of a ball of radius 3 centimeters is is 36 pi cubic centimeter. So that is an example of an evaluation of the function v. When the input is 3, we have evaluated the output to be this. Example 2, it need not always be something physical, of course. It can be a purely mathematical function. Suppose that the function capital F is defined for all real numbers t by the formula ft equal to 2 times t minus 1 plus 3. Evaluate capital F at these input values 0, 2, x plus 2 and f of 2. So since it's given like an exercise, so we write a solution. We just use the formula which is given to be the rule for the function, put the values of t here and calculate the corresponding outputs. F of 0 is 2 times 0 minus 1 plus 3. So that means 3 minus 2. So this is 1. F of 2 is 2 minus 1 is 1. 2 plus 3 is 5. F of x plus 2, where x can be any real number, is 2 times x plus 2 minus 1 plus 3, which is 2 times x plus 1 plus 3, and that equals 2x plus 5. And finally, here the input itself is f of 2. We have already calculated f of 2 to be 5. So this is 2 times 5 minus 1 plus 3. So 2 times 4 is 8, 8 plus 3 is 11. Okay, so that's how we just evaluate functions. Now the next thing is the domain convention. When we define a function, say y equal to f of x with a formula, with this sort of formula, and the domain is not stated, explicitly, then the domain is assumed to be the largest set of x inputs for which the formula, that is whatever we have here defining the function, that formula gives real y values. X inputs, or you can write x values also. And this largest possible domain is called the natural domain of the function. This is the so-called natural domain of the function f. If our domain is restricted to be something smaller than the natural domain, we have to explicitly mention that. If we want to restrict the domain in some way, we must say so. So what this thing says basically is that if we are given simply a formula, then, and nothing is said about the domain, then we have to assume the domain to be the largest possible set of real numbers, from which if you take a real number, use that as input in the function, you get a real number output. Okay, so and that largest possible domain is called the natural domain of the function. But if you want the domain to be smaller than the natural domain, then you have to explicitly mention that no, this is my domain, this is the restricted domain, here only I am going to concentrate or evaluate the function. Or in other words, This is the only set from which I am going to choose my inputs. Okay. So for example, the domain of the function this particular function, the square function, is understood to be the entire set of real numbers, because for every real number its square is again a real number, so all the real numbers can be considered as inputs. So the largest possible domain is the entire set of real numbers, so that is the natural domain of this function. The formula y equal to x square gives a real y value for every real x value. If we want to restrict the domain to values of x greater than or equal to 2, say, then we must use this additional condition, or more specifically, we must write the function like this. Y equal to x square, but only those real numbers x that are greater than or equal to 2. So this indicates that the domain is restricted. We are no longer considering all the real numbers, but only the real numbers that are greater than or equal to 2. So this is not the natural domain, or rather this is not the natural domain. The natural domain is the entire set of real numbers. It's only a proper subset of that. Changing the domain to which we apply a formula usually changes the range as well. For example, the range of simply this function y equal to x square, whose domain is the entire set of real numbers, is the set of all non-negative real numbers. Whereas the range of this function y equal to x square, where x is greater than or equal to 2 is the set of all real numbers greater than or equal to 4. So that is different. Example 3. Okay, let us take some formulas and try to see what the domain and range are in each case. Consider the function given by y equal to square root of 1 minus x square. Okay. The values of x for which y is real must satisfy this, because we have this square root, so we are not allowed to have a negative value inside the radical sign, because then the resulting thing won't be a real number anymore. It will become a non-real complex number. Anyway, it's not real number, so we require 1 minus x square to be non-negative. Now one minus x square is non-negative if and only if 1 is, in fact we have already solved this type of inequalities before, so let me just directly write what x will be. X has to belong to this closed interval minus 1 comma 1. So the natural domain, keep in mind here we are trying to find all the x's for which we get real y, so that means we are trying to find the natural domain. So the natural domain of the function is this closed interval. Now what about the range of this function? Let R be the range of the function one minus x square. Let y be any element in R. Then there exists that y, of course, is an output then, since it belongs to the range, so it has become an output because of some input x. So there exists x in the domain such that y is equal to this. Now since x is in this domain, so we can use these inequalities. -1 is less than or equal to x and x is less than or equal to 1. This implies x square cannot be negative, x square is non-negative and is itself less than or equal to 1. And this implies 1 minus x square is non-negative. Okay, that is true. That's not what I wanted to conclude. I wanted to conclude that this is in fact okay. Let us just complete this what we were writing anyway. So it's a non-negative real number, so its non-negative square root of course is also a non-negative real number. Also x square, whatever it is always greater than or equal to 0. This implies 1 minus x square is less than or equal to 1, and that implies we can now take square root on both sides, because 1 minus x square according to our choice is non-negative. Is less than or equal to square root of 1, which is 1. Thus y is greater than or equal to 0 and less than or equal to 1. That is, y belongs to this closed interval, but y was chosen to be any element in R. Therefore R is a subset of this closed interval. Conversely, let Z be any element in this closed interval. Okay, so okay, let me just think of the steps after this. So we want Z to be this, thus Z square is equal to 1 minus x square minus Z square. Then proceeding like above. Like above means, you see here, when x belongs to this closed interval, then x satisfied these things, that square root of 1 minus x square turns out to be less than or equal to 1, and it turns out to be greater than or equal to 0. Now when z belongs to 0, 1, z also belongs to -1, 1, because this interval is contained in this. So whatever we have found here for x, the same thing we can do for z. So that's why we are saying, then proceeding like above, we get this, that is we have got a real number in the domain Actually, this real number is really here. It is not negative, but after all, it is in the domain also, on the positive side, such that if we evaluate our original function at this real number, then what do we get? That is, if we calculate this, then note that here we have square root and square, so you can cancel them, but what you write after that matters, and that depends on the sign of 1 minus z square, whether it is positive or 0 or negative. We have already seen that 1 minus z square is non-negative, and that's why this is a real number in the first place, this square root. So after cancelling the square and square root inside, you get 1 minus z square itself. Or you can just simply, without thinking of that thing first at this step itself, about the sign of 1 minus z square, you can write 1 minus absolute value of 1 minus z square. But then you see that since 1 minus z square is non-negative, so its absolute value is 1 minus z square itself, and this becomes z square. Okay, now you use the fact that z itself is non-negative, so this is going to be z. So what does it tell us? It tells us that any element in this interval appears as the output of some input in the domain under our function. So every point in this interval is an output for our function. So this interval is contained in the range of the function. This implies this is a range element, and hence this is contained in the range. Now you combine these two inclusions. Thus R is equal to 0, 1. So we have found the domain, it is this, and the range, it is this for that particular function. This way there are three other functions which are somewhat easier than this one. I want you to find the domain and range in each case, and range of course is range, and the domain is natural domain. Okay, not just any other domain. One of them is this. Then the next one is this. And then okay, so for these three cases, you please calculate the domain and range in each case. You can ask me one question. Fine, the natural domain is the set of all, largest set of all possible x for which we get real y. What is the range? How to find, in fact, in this case, we simply sort of somehow know that the range is going to be this, and then we showed that that is indeed the case. But how does one guess the range in the first place? For that, you just note that the range is going to be the set of all possible y values. So looking at the formula for the function, you try to guess what y values are possible. So the set of all possible y values is the range. From there you can guess what the range is. Then of course you can use mathematical logic to prove that your guess is correct. After this we have graphs of functions, then even and odd functions, and many more things. So that we will see in the next part. So I end the calculus video here itself. If you want to say something about these things, you are free to write in the comment section, or you can mail me also here, which some of you are doing. I am very happy. At yahoo.com. So that will be all. So until the next part, it's me, Lucifer, from a mathematical room. Have a nice night.